In this segment, I want to talk a little bit about energy in collisions. So we've already talked about collisions, and we've learned how we can categorize collisions. We can categorize collisions as elastic or inelastic. And we've kind of put off exactly talking about that distinction until now. Elastic simply means that kinetic energy is conserved. In other words, the total kinetic energy of the system before the collision is exactly the same as the total kinetic energy after the collision. Now we know that in any collision, the total momentum beforehand is always the total momentum equal to the total momentum afterwards. So momentum's always conserved. But in an elastic collision, kinetic energy is also conserved. And so if we imagine what an elastic collision might look like, well, beforehand we've got, in this case, we've got ball number 2 at rest, although in general it could be moving. So beforehand we've got ball 2 at rest, and we've got ball 1 coming in here with some velocity, some initial velocity to the right, and they have some collision. Now during that collision, energy is stored in the molecular bonds within those balls. If we were to do a high-speed camera picture of this, we'd see that those balls were slightly deformed. They're no longer completely round. That energy is stored in the molecular bonds of the molecules that make up that ball. And as the balls expand back to their normal shape, that energy is released again in the form of kinetic energy. And so the kinetic energy beforehand is equal to the kinetic energy afterwards. Now what we can do, then we can take the equation that we've already used. Momentum final equals momentum initial. And of course we've got an m1 v1 initial and an m2 v2 initial and an m1 v1 final and an m2 v2 final in here, right? We've got that. We could also say this. Okay, so in an elastic collision, these two conditions are always met, right? We have momentum initial equals final momentum and kinetic initial equals kinetic final. I'll spare you the algebra, but the result is here, right? We can calculate the final velocity of the first ball and the final velocity of the second ball. This does assume, notice this is an important point here, it assumes that object 2 is initially at rest. So describing this situation right here, these are your equations. And it's just doing the algebra here. It's 2 equations and 2 unknowns. It's kind of hairy algebra. You could do it if you wanted to, but I won't make you do it. I'll just go ahead and give you the result. These problems tend to be kind of plug and chug, not too bad. So again, now we can categorize these collisions. We have elastic collisions, where momentum and kinetic energy are both conserved. So we don't lose any kinetic energy. Then we have inelastic collisions, where momentum is conserved, but we lose kinetic energy. And we have perfectly inelastic collisions, which is where the two objects stick together. So we know that if the two objects stick together, it's always inelastic. And so we can call that perfectly inelastic. And without even doing any math, we can say, hey, if the two objects stuck together, then there was some kinetic energy lost. Well, how much? Let's do a quick example to kind of see what kind of kinetic energy we expect to lose. It's a little bit surprising. An air track glider undergoes a perfectly inelastic collision with an identical glider that is initially at rest. What fraction of the first glider's initial kinetic energy is transformed into thermal energy in this collision? And what happened to the lost kinetic energy? Okay, so first off, let's just set up the situation, be sure we understand it, and then we'll see what the final velocity is for this air track glider, and that'll allow us to compare the energies. So, our initial situation, we have some glider with mass m coming in with some speed v, and it collides with some identical glider with v equals 0. So that's our initial situation. Our final situation is, since it's perfectly inelastic, we know they stick together, and they move off with some common velocity, v final. What is that final velocity? Well, we can do a real quick conservation of momentum problem. We'll do a standard coordinate system here. And so we'll start then with P final equals P initial. Since they do stick together, we can almost think of this as one object over here, right? So our final momentum then is simply 2m times v final. Our initial momentum is simply m times v. Notice my m's cancel, And I get the not terribly surprising result that V final equals the initial velocity over 2. So, in other words, it lost half of the initial velocity, right? So it comes out with half the velocity. How does the kinetic energy compare? Let's see that, okay? So we're going to do kinetic energy initial. Well, that's 1/2 mv squared, right? And without any numbers, that's kind of as far as we can take it. How about the final kinetic energy? We have final kinetic energy is 1/2 times 2m times v over 2 squared. Well, when we do this out, we end up with 1/2 of 1/2 mv squared, or notice that, and notice the second 1/2 right here, it came from, the 2 squared on the bottom is 1/4. 2 times 1/4 is 1/2, right? And so notice then that we can write this as 1/2 of the initial kinetic energy. So if we finish with 1/2 of the initial kinetic energy, well, notice what the question asks. The question asks, how much did we lose? If we kept 1/2, well, then we lost 1/2. So we lost K initial over 2. Okay. So, in other words, we lost half of the kinetic energy that we started with. That's the answer to part A. Well, what about part B? What happened to the lost kinetic energy? It turned into thermal energy, didn't it? Right? So it didn't just go away, right? Conservation of energy tells us it definitely did not just go away. But what did it do? Well, it turned into thermal energy. So our gliders are slightly warmer for having had this collision.